What if the universe whispers, not in words, but in events, in moments of impossible synchronicity that defy all our calculations of chance? We look out into the void and see a clockwork of gravity, a predictable dance of orbits and spins governed by laws as old as time itself. But every now and then, two dancers who should never have shared a stage find themselves locked in a sudden violent embrace. This is the story of one such moment, a cosmic riddle that pits the cold logic of probability against the unnerving possibility of a connection we never dreamed existed. It begins with a world you think you know, a world of rust-coloured silence. Mars. For millennia it has been a beacon in our night sky, a crimson wanderer fueling our myths and our ambitions. To us it is the next frontier, the stepping stone to the stars. Yet up close, it is a world of profound and ancient solitude. Imagine standing there on the floor of Gale Crater beside the quiet hum of a rover that is our sole emissary in this alien desert. The silence is absolute, a pressure so low it feels less like an atmosphere and more like the memory of one. The sky above is not the rich blue of home, but a thin butterscotch veil barely substantial enough to scatter the light of a distant, smaller sun. This is a planet holding its breath. You see a world etched by a history of unimaginable violence and heartbreaking loss. The colossal gash of Valles Marineris, a canyon system that would swallow its terrestrial counterpart whole, speaks of tectonic forces that tore the planet's crust asunder in its youth. The towering edifice of Olympus Mons, a shield volcano so vast its peak pierces the tenuous atmosphere, stands as a monument to a fiery, geologically vibrant past. These are the scars of a world that was once alive, a world that once pulsed with heat and energy. Now they are silent relics, sleeping giants under a pale sky. Look closer and you can trace the ghosts of water, the meandering channels of ancient riverbeds, the smooth, worn stones in a long dry lake, the sprawling deltas where water once poured into vast basins. Billions of years ago, this rusty desert may have been a blue world, a place with clouds, with rain, with oceans. A place perhaps not so different from our own. That world is gone, stripped away by the relentless solar wind after its protective magnetic field died. What remains is a planet caught between life and death, a cryogenically frozen museum of what might have been. Its energy now comes in whispers. You can see it in the seasonal ebb and flow of its polar ice caps, great white swirls of frozen water, and carbon dioxide that breathe with the Martian year. You can feel it in the subtle tremors detected by our landers, the faint, deep heartbeat of a planet not yet entirely cold. And you can witness it in the winds, the only true source of motion and change on this sleeping world. These winds, born from the simple differential heating between the sunlit equator and the frigid poles, are the architects of modern Mars. They sculpt the dunes into majestic flowing seas of sand. They scour the rocks, revealing layers of geologic time. They carry the fine, ubiquitous dust that clodacks the entire planet in its signature shade of red. This dust is the lifeblood and the terror of Mars. It is composed of microscopic particles of iron oxide rust, so fine it clings to everything, a permanent red stain on our robotic explorers. In the thin air, this dust can be whipped into towering columns, spinning vortices of grit we call dust devils. These are the planet's ephemeral ghosts, dancing across the plains for a few fleeting moments before dissolving back into the landscape. For most of the Martian year, this is the extent of the planet's fury. Localized squalls, regional hazes, a predictable pattern of atmospheric activity that our orbiters have mapped for decades. We came to believe we understood the rhythm of Mars, its seasons of calm, and its predictable periods of atmospheric unrest. We knew that every few Martian years something more dramatic could occur. A regional storm might spiral out of control, a chain reaction of dust lifting that could cover an entire hemisphere. And then, once or twice a decade, the planet awakens in a true cataclysm, a global dust storm. This is not weather, it is a planetary transformation. It begins perhaps in the deep chasms of the Hellas Basin, where sunlight warms the floor and sends superheated air surging upwards. The initial disturbance is small, but it feeds on itself an atmospheric avalanche in slow motion. The airborne dust absorbs more sunlight, warming the air around it, creating even stronger winds that lift yet more dust. A feedback loop is born. Within days, a localized storm becomes a continent-sized tempest. Within weeks, the individual storms merge into an unstoppable, unified weather system, a single planet-encircling shroud of ochre cloud. From space, the change is breathtaking and horrifying. The familiar detailed tapestry of canyons, craters, and volcanoes vanishes. Mars ceases to be a world of geology and becomes a featureless, malevolent orb, its surface completely obscured by a roiling, opaque blanket. For the lonely rovers on the ground, it is the arrival of a long, dark night. The sky, once a pale pink, darkens to a bruised blood-orange twilight that persists even at noon. Sunlight, their very source of life, is choked off, reduced to less than 1% of its normal intensity. Temperatures plummet. The wind, now a constant mournful howl, carries a fine, abrasive grit that seeks out every joint and mechanism. This is Mars unleashed, a reminder that this silent, beautiful world holds within it a capacity for suffocating, world-altering violence. It is an event so profound, so all-encompassing, that it fundamentally changes the planet for months on end. And we believed these events rare, as they were belonged only to Mars, that they were a product of its own delicate internal machinery. We were wrong, because while Mars was preparing for its great convulsion, something else was approaching. A traveler from an impossible distance. It wasn't a familiar neighbor from the asteroid belt, nor a returning wanderer from the icy Oort cloud that encircles our own solar system. This was something other, an outcast from another star. We call it 3I, Atlas. The I stands for Interstellar, a designation of profound significance, a label that separates this object from the trillions of others that call our solar system home. This was only the third such visitor ever detected in all of human history, a ghost slipping through our celestial living room before vanishing forever. Imagine its journey, born in the swirling disk of gas and dust around a star you will never know the name of, in a constellation you cannot see. It is a primordial remnant, a frozen piece of a solar system that might be utterly alien to our own. Perhaps it was flung out of its home by the gravitational shove of a giant planet, a game of cosmic billiards that exiled it to the cold, dark wilderness between the stars. For eons it travelled, millennia stretching into millions, perhaps even billions of years. A solitary frozen projectile tumbling through the interstellar medium, a space so empty it makes the void between our own planets seem crowded. The light from our sun would have been just another anonymous star among countless others, a destination unknown and unintended. Then by sheer dumb luck, its trajectory brought it into our sun's gravitational well. It began to fall, accelerating silently out of the darkness. As it crossed the orbit of Neptune, then Uranus, the distant sun's warmth began to stir it from its long slumber. This was no inert rock. It was a comet, a dirty snowball of ancient ices, dust, and organic molecules. The sun's radiation began to sublimate its surface, turning solid ice directly into gas. A faint ethereal shroud, a coma, began to bloom around its frozen nucleus. It grew a tail, not one, but two. A brilliant white dust tail composed of particles pushed away by the pressure of sunlight itself, tracing the comet's curved orbital path, and a second, fainter blue ion tail made of charged gas blown straight away from the sun by the solar wind, acting as a celestial weather vane. Its beauty was hypnotic, a stark contrast to the brutal spectacle unfolding on Mars. Where the Martian storm was opaque, violent, and suffocating, the comet was translucent, graceful, and silent. It was a celestial brushstroke against the velvet black of space, a transient spectacle of stunning elegance. Its composition was a treasure trove of information, a chemical fingerprint of its unknown birthplace. Spectrographs revealed the presence of familiar compounds like water and carbon monoxide, but also hinted at isotopic ratios and molecular abundances that were subtly yet distinctly not of our solar system. It was a messenger carrying a postcard from a star we may never visit, a tangible piece of another world delivered right to our doorstep. We tracked its path with every telescope we could muster, charting its inbound trajectory with breathtaking precision. And as we did, a startling, impossible alignment began to emerge from the data. The timing was exquisite. As the fledgling dust storms in the southern hemisphere of Mars began their inexorable merger into a planet-killer 3I, Atlas was screaming towards its perihelion, its closest approach to our sun. Its path was fated to carry it close, exceptionally close to the orbit of Mars. Not on a collision course, but close enough for a whisper, a fleeting interaction across the vacuum of space. The two events, one a planetary tantrum born from within, the other a silent celestial passage from without, were converging in time and space with a precision that felt scripted, choreographed. The global storm on Mars reached its peak intensity, the planet's atmosphere becoming a fully opaque, turbulent maelstrom at the very same moment, the very same week, that the interstellar comet made its nearest pass to the red planet. Think about the odds. A planet-encircling dust storm, an event that might happen only once a decade, erupting in perfect synchrony with the flyby of an interstellar comet, an object so rare we've only ever seen 3 of them in total. It is a coincidence of such staggering improbability that it forces us to question the very definition of the word. Science is built on the bedrock of cause and effect, on the principle that events are linked by physical, measurable mechanisms. But what mechanism could possibly connect a 4.5 billion-year-old planet to a transient visitor from another star system, separated by millions of kilometers of empty space? It seems like a fantasy, a plot from a science fiction novel, a planet reacting to the presence of an alien object. Yet the data is undeniable. The timing is a fact written in the cold, hard numbers of orbital mechanics and atmospheric telemetry. This is the mystery that stands before us. Was this truly the universe flipping a coin and having it land on its edge 1,000,000 times in a row, a fluke of cosmic chance so profound that we will never see its like again? Or did we witness something new, a form of interaction between celestial bodies that we have yet to understand? Did the comet, a visitor trailing its own atmosphere of dust and gas, somehow seed the Martian sky? Imagine its tail, a gossamer ribbon of microscopic particles stretching for millions of kilometers washing over Mars. Could these alien dust grains have acted as nuclei, as triggers for cloud formation in the thin Martian air, initiating a cascade that led to the global storm? It's a tantalizing, almost heretical idea. Or perhaps the connection was more subtle, more invisible. Comets, as they interact with the solar wind, generate their own complex magnetic fields, a bubble of plasma that surrounds them. Mars, having lost its own global magnetic shield, is left vulnerable. Could the comet's magnetosphere have draped itself over the planet during its close pass, creating an electrical connection? A circuit across space that dumped energy into the upper atmosphere, disrupting its delicate equilibrium and providing the spark that ignited the planetary firestorm below. We are entering a realm where the boundaries between atmospheric science, plasma physics, and planetary geology begin to blur. A territory where we must be willing to entertain extraordinary possibilities. This is not a journey into speculation. It is a scientific investigation, a detective story written on a planetary scale. The crime scene is an entire world. The suspect is a fleeting phantom from another star. The clues are buried in petabytes of data from our orbiters, hidden in the light spectra from the comet's tail and locked within the complex computer models that simulate the behavior of a world's atmosphere. To find the truth, we must peel back the layers of this extraordinary celestial convergence. We must journey deep into the heart of a Martian dust storm to understand the forces that can turn a planet from a tranquil desert into a raging inferno. We need to chase the ghost of 3i Atlas, dissecting its composition and behavior to understand what power, if any, it might have wielded. We are about to embark on that odyssey. We will stand with the scientists who first saw the connection, who dared to ask the impossible question. We will explore the cutting-edge physics that might explain the unexplainable. We will weigh the evidence for a cosmic coincidence against the evidence for a cosmic connection. The answer will not only solve the riddle of one Martian storm, it will redefine our understanding of how worlds interact. It will tell us if planets are truly isolated islands in the cosmic sea, or if they can be touched, influenced, and fundamentally changed by the silent passage of strangers from the dark. The verdict is not yet in, and the stakes are nothing less than our perception of the living, breathing interconnectedness of the universe itself. Of all the worlds we have ever known, of all the points of light we have traced across the heavens, perhaps none holds our imagination quite like Mars. It exists in our collective mind as a paradox, a world both intimately familiar and profoundly alien. You can see it on a clear night, a steady, ochre-hued lantern burning in the cosmic dark, a silent neighbour on its own lonely orbit. But this silence, this apparent serenity we perceive from tens of millions of miles away, is a profound deception. Mars is not a dead world. It is a world that sleeps, and its dreams are of unimaginable violence. It breathes, but its breath is a razor-thin atmosphere of carbon dioxide, a fragile veil barely clinging to a planet that has lost almost everything. And when this world stirs, it does so with a fury that can rewrite its own face. We have learned through the tireless eyes of our robotic emissaries that Mars is a planet of profound and savage weather. Its tranquility is merely an intermission between acts of geological and atmospheric drama on a scale that dwarfs anything on Earth. The true monster in the Martian climate system is not the cold which plunges to depths that would freeze carbon dioxide from the air. It is not the wind, though it scours the surface with hypersonic grit. The true monster is the dust. Fine as smoke, sharp as ground glass, and coloured with the rust of a world's long decay, this ferric dust is the lifeblood of the Martian atmosphere. It is the pigment that gives the planet its signature colour, and it is the fuel for its most terrifying spectacle, the global dust storm. These are not mere weather events, they are planetary seizures. They are a seasonal ritual of self-immolation, a reminder that even a world with an atmosphere 100 times thinner than our own can conjure a tempest capable of swallowing a planet whole. For this to happen, a perfect conspiracy of celestial mechanics and atmospheric physics must unfold. It begins with the planet's own orbit, an elliptical path that brings it significantly closer to the Sun at one point in its long 687-day year. This point, its perihelion, is the trigger. During this southern hemisphere summer, the sun's faint warmth intensifies just enough to sublimate the vast polar caps of frozen carbon dioxide. This sudden release of gas into the thin atmosphere creates immense pressure differences, a planetary scale imbalance that gives birth to ferocious winds. Down in the great impact basins like the colossal Hellas Planitia, the air, now energized, begins to move. It starts small. A localized thermal updraft, a dust devil twisting across the barren plains, a seemingly insignificant plume of red dust kicked into the sky. But in the thin Martian air, dust particles have a peculiar quality. Once airborne, they absorb sunlight, warming the pocket of atmosphere around them. This warmer air rises, creating lower pressure beneath it, which in turn pulls in more surrounding air, creating stronger winds. Those stronger winds lift even more dust. It is a terrifying positive feedback loop, a meteorological chain reaction. A spark has found a planet-sized tinderbox. What began as a regional storm now begins to metastasize. The winds, no longer localized, feed the growing storm front, which expands with astonishing speed. Within days, it can encircle an entire hemisphere. Within a week or two, the transformation is complete. Individual storms coalesce into a single monolithic planet-enshrouding entity. From space, all of Mars's familiar features, the soaring peak of Olympus Mons, the grand scar of Valles Marineris, the pale expanse of the polar caps, all of it vanishes beneath a churning, homogeneous, butterscotch-coloured haze. The planet becomes a featureless orb, a world erased. For any machine unfortunate enough to be caught on the surface, the experience is apocalyptic. The sky, once a pale pink or a faint tan, deepens to a bruised blood red. Then, as the dust column grows to tens of miles in thickness, it darkens further, plunging the world into a perpetual twilight and finally into an impenetrable Stygian blackness. Sunlight, the life force for our solar-powered explorers, is extinguished. We learn this lesson in the most heartbreaking way imaginable. For 15 years, our intrepid rover, Opportunity, had roamed the plains of Meridiani Planum, a testament to our ingenuity and our thirst for knowledge. It had survived dust storms before hunkering down rationing power, waiting for the skies to clear. But in 2018, it faced the beast. As the storm gathered, Opportunity's human pilots watched helplessly from Earth as the light levels plummeted. The rover's solar panels, which had faithfully drunk in the faint Martian sunlight for over a decade, were now starved. The energy flowing into its batteries dwindled from a healthy trickle to a desperate whisper, and then to nothing. The last message it sent was a simple, poignant packet of data, a final report from the darkness. "My battery is low and it's getting dark. and then silence. For months we waited, we listened. The team at the Jet Propulsion Laboratory sent thousands of commands playing songs to wake the rover, hoping that a gust of wind might miraculously clear its panels. It was a vigil for a machine we had come to love, a vigil held across the gulf of interplanetary space. But no reply ever came. Opportunity now stands as a silent monument, a hero of exploration entombed by the very world we sent it to understand, buried beneath the dust of a global storm. This is the Mars we know, a world of epic beauty and even more epic violence, a planet locked in a cycle of seasonal fury. Its global dust storms are a known quantity, a predictable if devastating part of its natural rhythm. So when the skies began to darken again in the Martian autumn of 2022, it was at first not a surprise. It was the season for it. It was Mars being Mars, but this time something was different. This time, as the planet began to choke on its own dust, it was not alone. A traveler was passing through the neighborhood, a ghost from the interstellar dark. Its name was 3I, Atlas, and it was an object so strange, so utterly alien that it challenged our understanding of what was possible. It was not from around here, and we mean that in the most literal sense imaginable. It did not belong to our solar system. It was born in the swirling disk of gas and dust around a completely different star, a star that we will likely never identify, located in a direction we can only guess. It was discovered, as many such objects are today, by an automated sentry. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, a pair of robotic telescopes in Hawaii, scans the sky relentlessly for anything that moves. In the endless stream of data, a faint fuzzy smudge appeared, an object on a trajectory that at first seemed unremarkable. But as observatories around the world turned their gaze upon it, and as mathematicians refined its orbit, a startling truth emerged. The object's path was not a closed ellipse, the familiar gravitationally bound loop of a planet or an asteroid. It was a hyperbola, a path that was wide open. This meant it was moving far too fast to be captured by our sun's gravity. It was not circling our star, it was executing a single majestic high-speed flyby. It had fallen out of the interstellar void, would swing once around our sun, and then depart, vanishing back into the endless night between the stars, never to return. It was only the third such interstellar object ever definitively identified, a fleeting emissary from another star's family, and it was deeply, profoundly weird. We expect comets, even interstellar ones, to be a certain way dirty snowballs, as the famous analogy goes, conglomerations of ice, rock and dust. When they approach the sun, the heat sublimates the ices, creating a glowing coma and a spectacular tail. 3I. Atlas, however, refused to play by the rules. As it neared our system, it didn't just develop a tail, it began to disintegrate. Not in a single explosive event, but in a strange, protracted process of shedding fragments as if it were sloughing off its very substance. Spectroscopic analysis, which reads the chemical fingerprint of light reflected from an object, returned baffling results. It seemed to possess an unusual composition, perhaps richer in certain metals or exotic frozen gases than the comets born in our own Oort cloud. It was a shard of a long-dead alien world, and it was behaving erratically like a cosmic artifact, reacting unpredictably to the unfamiliar environment of our star system. It was a puzzle, a ghost in the machine of the solar system, an object that raised far more questions than it answered. Astronomers, both professional and amateur, were captivated. Here was a genuine piece of another solar system delivered right to our doorstep. Telescopes tracked its every move, documenting its strange, slow-motion self-destruction, trying to decipher the secrets it held about its distant birthplace. It was a moment of pure scientific wonder, the study of an object that had travelled for millions, perhaps billions of years through the cold and the dark, only to briefly grace us with its presence. Its trajectory was meticulously plotted, a graceful hyperbolic arc that would carry it inside the orbit of Mars, relatively close to the red planet, on a cosmic scale, before it whipped around the sun and began its long journey back out into the galaxy. The scientific community was buzzing, focused entirely on the unique nature of this interstellar guest. The unfolding events on Mars, the gathering dust storm, were for the moment a separate story, a different television channel. It was a known Martian phenomenon occurring at the same time as a rare celestial visitation. two spectacular but entirely unrelated events. But then, as the data from both phenomena were laid side by side, a few curious minds began to notice something. A coincidence. A chillingly precise coincidence. The Martian global dust storm, the very event that would ultimately lead to the silencing of yet another of our rovers. The InSight lander didn't just happen in the same season as the comet's passage. Its genesis, the initial explosive expansion from a regional disturbance into a planet-choking monster, occurred almost exactly as 3I, Atlas, made its closest approach to the red planet. The two timelines, that of the alien comet and the native storm, were not just parallel, they intersected with uncanny precision. In the halls of universities and the remote control rooms of space agencies, the first whispers began. It started not as a theory, but as a question, a thought exercise uttered in hushed tones. What if? What if these two events were not separate dramas playing out on the same stage? What if one had triggered the other? The immediate orthodox response was, of course, skepticism. And for good reason. Science at its best is a discipline of rigorous doubt. Correlation, as every scientist knows, does not imply causation. Mars has global dust storms all the time. It was the right season for one. The comet just happened to be passing by. To suggest a link was to venture into the realm of speculation, to propose a physical mechanism that was at best unproven. How could a distant comet, even an interstellar one, possibly influence the atmosphere of an entire planet? The distances were still vast. The comet's solid nucleus was small. Any interaction would be unimaginably tenuous. It had to be a coincidence. It was the only rational explanation. It was the only explanation that fit within the known laws of physics and planetary science. And yet, the timing was just too perfect. The alignment was too poetic, too suggestive to be ignored completely. The thought, once spoken, could not be entirely unsaid. It lingered in the air, a tantalizing, almost heretical possibility. The idea was like a seed planted in the fertile ground of scientific curiosity. Perhaps the comet's enormous diffuse tail, though nearly invisible, had brushed the upper layers of the Martian atmosphere. Could the dust particles from this alien object carrying a different electrical charge or composed of a unique mineralogy have seeded the clouds and disturbed the atmospheric equilibrium? Or could it have been a magnetic interaction, ripple in the solar wind caused by the comet's passage that cascaded down into the thin Martian air, providing the energetic nudge that pushed a brewing storm over the edge into a global cataclysm? These were wild, unsubstantiated ideas, the first tentative steps into the dark, but they represented a paradigm shift in thinking. We have always thought of planets as islands, their weather systems self-contained, influenced only by their star. The notion that a passing vagabond from another star system could reach out and touch a planet to physically alter its climate was a concept straight from the pages of science fiction. Was this then merely a grand coincidence of cosmic proportions? A chance alignment of two unrelated cycles of nature, one Martian, one interstellar? Or did we, through our telescopes and robotic eyes, witness something truly profound, an act of planetary interaction we had never before imagined? A fleeting, violent conversation between a sleeping red world and a mysterious traveller from the endless void. To find the answer, we would need to sift through the data with new eyes, to challenge our old assumptions, and to follow a trail of evidence that was as tenuous and ephemeral as the tail of the comet itself. The stage was set for a scientific mystery, one that began with a dead rover and a ghost from another star. From a planetary whisper, the storm had found its voice, a voice that was now becoming a deafening planet-encompassing roar. What began as a localized disturbance in the northern plains was now staging a relentless coup against the Martian climate, its tendrils of dust reaching, grasping and coalescing with an almost biological imperative. You are watching a world being erased. From the silent, godlike perch of the Mars Reconnaissance Orbiter controllers at the Jet Propulsion Laboratory could only observe as familiar landmarks the sprawling canyons of Valles Marineris, the towering peak of Olympus Mons. Pale expanse of the polar caps began to flicker and fade, surrendering to a burgeoning, featureless veil of ochre. The planet was pulling a shroud over its own face. On board the orbiter, an instrument called the Mars Climate Sounder was working overtime, taking the temperature of the escalating crisis. Its data streams painted a truly dramatic picture of atmospheric chaos. As the dust particles lofted miles high absorbed incoming sunlight, the upper atmosphere began to heat up by tens of degrees. This wasn't a gentle warming, it was a fever spike, a thermal shockwave propagating through the tenuous air. Below this heated layer, the surface, now starved of the sun's energy, was paradoxically beginning to freeze. A planet-wide temperature inversion was taking hold, a bizarre and violent rearrangement of the fundamental laws that governed the Martian environment. This thermal chaos was the engine of the storm, creating ferocious winds that picked up yet more dust, feeding the very monster that spawned them in a terrifying feedback loop. The storm was no longer just a weather event. It had become the architect of its own terrifying growth, a self-sustaining atmospheric machine of immense power. Lower in orbit, the European Space Agency's Mars Express confirmed the scale of the cataclysm. Its sensitive spectrometers, designed to parse the subtle chemical fingerprints of the atmosphere, were instead blinded by the sheer density of the dust. The signals were swamped, the data saturated with the signature of airborne silicate minerals. It was like trying to identify a single person's whisper in the middle of a rock concert. But even this overwhelming noise told a story, the story of a planet's surface being physically lifted into its sky, of geology becoming meteorology on a scale almost impossible to comprehend. Meanwhile, NASA's MAVEN orbiter, whose mission is to study the upper atmosphere and its escape into space, registered something equally profound. The entire atmospheric column was expanding, swelling upwards, like a loaf of bread as it heated. The boundary between atmosphere and space itself was being pushed outwards by the storm's fury, accelerating the loss of precious gases into the void. Mars was bleeding its atmosphere, and this global storm was opening the wound wider. And what of our robotic emissaries on the ground, our eyes and hands on this now hostile world? For the Curiosity rover in Gale Crater and Perseverance in Jezero, the sky had fallen. Their worlds shrank to a few dozen meters of hazy, amber-tinted gloom. The sun, once a sharp, brilliant disk in the thin air, was reduced to a faint, ghostly smudge, a watercolor impression of its former self. Mission controllers watched the light-level readings, what scientists call the tau, plummet with alarming speed. Each day, the rover's solar panels gathered less and less energy, their lifeblood from a star 140 million miles away, being choked off photon by photon. The engineering teams, seasoned veterans of Martian winters and past dust storms, began enacting contingency plans. Non-essential science operations were halted. Spectrometers were powered down, robotic arms were placed in safe resting positions. The rovers were being put into a state of forced hibernation, their intricate minds focused on one single overriding command: survive. Survive the long, dark twilight. Survive the cold. And listen. Listen through the wind and the dust for a signal from home, a promise that this too shall pass. They became silent steel monuments, patient witnesses to an ancient planetary rage trapped inside the belly of the beast. Simultaneously, as Mars fought its internal war, another drama was playing out across the gulf of interplanetary space. Its protagonist, a visitor from the deepest, coldest recesses of the solar system. Here on Earth, under the clear, dark skies of Chile and Hawaii, the world's most powerful telescopes turned their gaze not towards Mars, but towards the ghostly interloper, Comet 3I, Atlas. Through their lenses, it was no longer an abstract point of light, but a celestial entity with a life of its own. It wore a magnificent coma, a vast, glowing shroud of gas and dust, sublimating from its icy heart, an atmosphere many times larger than the planet Jupiter. Trailing behind it, a gossamer tail of ionized gas pushed back by the solar wind, stretched for millions of miles, a delicate, ethereal banner pointing directly away from the sun. It was a beautiful, almost serene spectacle, a cosmic wanderer on its long-appointed journey through our neighborhood. But this serene image was deceptive. The comet was in trouble. As it plunged closer to the sun, the gentle warming it had experienced in the outer solar system was becoming a relentless thermal assault. The sun was no longer a nurturing warmth, it was a celestial blowtorch. Astronomers began to notice subtle but significant changes. The comet's brightness, which had been steadily increasing as predicted, suddenly began to plateau, then flicker erratically. Its nucleus, a fragile agglomeration of ice, rock, and primordial dust no more than a few kilometers across, was starting to buckle under the strain. The jets of outgassing material which created its beautiful coma were also acting like chaotic, unpredictable rocket thrusters, putting an immense rotational stress a torque on the nucleus. It was a gravitational gyroscope spinning itself into oblivion. Then it happened. Over a period of days, high-resolution images revealed the terrible, silent truth. The single, sharp point of light at the heart of the coma had fractured. It broke apart not in a single violent explosion, but with a kind of sad, graceful dissolution. First into 2 pieces, then 4, then a dozen or more. Comet 3I, Atlas, was dying. It was disintegrating before our very eyes, its ancient frozen heart shattering into a ghostly retinue of fragments, each piece embarking on its own slightly different trajectory, a funeral procession continuing along the original orbital path. We were witnessing the end of a journey that had begun billions of years ago in the Oort cloud. This ephemeral messenger, which had travelled for eons to pass by Mars at this exact moment, was now little more than a string of icy pearls, a phantom of its former self bleeding its substance into the vacuum of space. Its hydrogen, its water, its organic compounds, the very building blocks of life, were now spread across a vast corridor of space, a corridor through which Mars was inexorably flying. Back in the control rooms and science labs on Earth, 2 narratives, 2 sets of data streams were now flowing in concurrently, creating an extraordinary and perplexing juxtaposition. On one screen, a planet was disappearing under a blanket of dust. On the other, a comet was dissolving into a cloud of gas and ice. The timelines were not just similar, they were uncannily precisely aligned. The storm's most rapid phase of global expansion coincided almost perfectly with the comet's fragmentation and its closest approach to the red planet. For the scientists, this presented a monumental challenge, a puzzle wrapped in an enigma. The immediate instinctive response of any rigorous scientific mind is to assume coincidence. It is the bedrock of scientific discipline, the null hypothesis. You do not invoke a new or extraordinary cause when a perfectly ordinary one will suffice. And Mars, after all, is the planet of dust storms. Global planet-encircling events are not an anomaly. They are a known, if not perfectly understood, part of its climate cycle occurring every few Earth years. It was entirely possible, indeed probable, that we were simply witnessing 2 independent dramatic astronomical events unfold at the same time. The universe, after all, has no obligation to avoid narrative convenience. This was the official cautious position. The storm was following a pattern, albeit a particularly ferocious one, that had been seen before. In 2007, a similar storm threatened the rovers Spirit and Opportunity. In 2018, another colossal tempest engulfed the planet, ultimately leading to the demise of the Opportunity rover as it was starved of sunlight. Mars does this. It has a temper. The physics of its thin atmosphere, its extreme temperature swings, and the particular properties of its fine reddish dust create a system perpetually on the brink of chaos. It only needs a small nudge, a localized storm in just the right place, at just the right time, to trigger a cascading failure that blankets the entire globe. From this perspective, the passage of Comet Atlas was pure, spectacular cosmic theatre, nothing more. It was a dramatic backdrop to a quintessentially Martian drama, a chance alignment that would be noted in textbooks as a remarkable curiosity. For most of the science community, this was the end of the story. Case closed. But for a few, a nagging, tantalizing question remained. What if? What if the universe wasn't being so narratively simple? What if the alignment wasn't a coincidence at all? The question was scientific heresy to some, a thrilling possibility to others. How could a comet, even a large one, influence an entire planet's atmosphere from over 10 million kilometers away? The gravitational pull would be negligible, infinitesimal. It couldn't raise tides in the atmosphere or exert any kind of direct physical force. There was no known mechanism, no established physics that could link these 2 events. And yet the timing was so perfect, so incredibly precise, that it felt intellectually negligent to dismiss it out of hand without at least exploring the very fringes of atmospheric science. A new speculative line of inquiry began to emerge, not in official press releases, but in the hushed, excited conversations between atmospheric modelers and planetary scientists. They began to ask, could the comet have provided the nudge? Could it have been the finger that tipped the first domino? The hypotheses that began to form were subtle, elegant, and deeply theoretical. They didn't rely on brute force, but on a far more delicate interaction. The focus turned to the one thing the dying comet was releasing in prodigious quantities: hydrogen. As the comet fragmented, it released its trapped water ice, which was immediately broken down by the sun's ultraviolet radiation into its constituent parts, oxygen and hydrogen. MAVEN had already shown that Mars is constantly losing its own atmospheric hydrogen to space. Now, with the comet's passage, the planet was flying through a region of space anomalously enriched with this same element. The planet was bathing in the comet's ghost. The theory went like this: this influx of cometary hydrogen, though incredibly tenuous, could have penetrated the upper reaches of the Martian atmosphere. There, in the frigid high-altitude regions, it would have encountered the diaphanous, wispy clouds of water ice that we know exist on Mars. This is where the truly novel science began. In Earth's atmosphere, the formation of clouds often requires a seed, a tiny particle of dust, salt, or pollution for water vapor to condense upon. This process is called nucleation. The radical new idea was that these incoming hydrogen atoms could have acted as an incredibly effective widespread nucleation seed for the high-altitude ice clouds on Mars. The sudden abundance of these seeds could have triggered a rapid planet-wide efflorescence of these clouds, causing them to become thicker, more expansive, and more reflective than they would have been otherwise. This wouldn't seem like much, but in a climate system as delicately balanced as that of Mars, it could have been the crucial perturbation, the first domino in a long and complex chain. A sudden change in high-altitude cloud cover would fundamentally alter the way the atmosphere absorbed and radiated heat. It would change the temperature gradients, the pressure differences, the very dynamics that keep the great wind systems in a state of equilibrium. Imagine it not as a push, but as a change in the rules of the game. The atmosphere was already primed for a global storm. The ingredients were all there, but the cometary hydrogen might have created a new, unstable atmospheric state, subtly altering the thermal balance and making the transition to a global storm not just possible but inevitable. It didn't light the fire, but perhaps it soaked the kindling in gasoline. It was a breathtaking, audacious idea, a mechanism connecting the death of a comet to the rage of a planet's weather. It was a ghost reaching across millions of miles of empty space to stir the air of another world. And it posed a profound and immediate challenge to the teams monitoring the situation. Buried somewhere in the torrent of data pouring back from MAVEN and the Mars Express orbiter, there might be a clue, a chemical fingerprint. Could they detect an anomalous spike in hydrogen in the upper atmosphere? Could they distinguish that hydrogen, the comet's hydrogen, from the planet's own native supply? The race was now on, not just to monitor the storm's fury, but to conduct a planetary-scale forensic investigation, searching for the faint ephemeral signature of a celestial visitor that might have been far more than just a passive bystander. The mystery had just deepened immeasurably. And so the official explanations, tidy and conventional, fell short. They failed to quiet the nagging voice of coincidence, a cosmic synchronicity so perfect it felt almost deliberate. For a small, audacious fringe of the scientific community, the close pass of Comet 3I, Atlas, and the subsequent birth of a planet-killing storm on Mars was not a case to be closed, but a mystery to be cracked open. To even suggest a link was to invite professional ridicule to step beyond the pale of accepted atmospheric science. It was to propose that a ghost in the interplanetary night could somehow reach out and stir a world to fury. Yet science at its best is not about comfort. It is about the relentless pursuit of uncomfortable questions. The question that refused to die was not times if times the events were connected, but times how asterisk. How could a distant, ethereal wanderer, a transient visitor of ice and rock, possibly command the weather of an entire planet millions of kilometers away? The chasm between the two events was immense, a void of cold, silent space. To bridge it would require a new kind of physics, a new understanding of the delicate interplay between worlds. Investigators turned their focus from the grand spectacle to the infinitesimally small, to the unseen tendrils of the comet itself. Every comet you see is a messy traveler. It doesn't just glide through the solar system, it sheds. For eons, 3i, Atlas, had been bleeding a continuous invisible trail of debris into space, a ghostly procession of microscopic dust, grains, and frozen gases, each no larger than a particle of smoke. This vast, ethereal river of cosmic dust, its tail would have swept directly across the orbital path of Mars. The planet, in its inexorable journey around the Sun, would have had no choice but to plunge directly through it. This was not a hypothesis, it was a certainty. Mars had bathed in the spectral remains of its visitor. The real question was whether this cosmic shower could have been the spark. This led to the first and perhaps most compelling of the radical new theories, the idea of micrometeoroid seeding. Imagine the Martian atmosphere, a system perpetually on a knife's edge. It is thin, fragile, and choked with fine red dust, a global tinderbox awaiting a match. For a dust storm to begin, something needs to kick that dust upwards. Localized heating can create dust devils, tiny whirlwinds that serve as the embryos of larger tempests. But for a storm to go global, you need countless triggers, a coordinated ignition across vast regions of the planet. Here, the comet's tail offered a tantalizing, almost poetic solution. Scientists proposed that as Mars plunged through this stream of cometary debris, billions upon billions of these microscopic particles would have rained down into the upper atmosphere. They wouldn't have burned up like dramatic meteors. They were too small for that. Instead, they would have drifted down, silent and unseen. These particles were not just inert dust. They were in essence foreign contaminants, perfect little anchors for atmospheric chemistry. They could have acted as what scientists call condensation or nucleation sites. In the frigid heights of the Martian sky, the sparse water vapor present would have found these alien grains irresistible. Ice crystals would begin to form around them far more efficiently, and at higher altitudes than they normally would. The formation of these high-altitude ice clouds would have fundamentally altered the energy balance of the atmosphere above the dust layer. These clouds reflect sunlight differently, absorb heat differently. They are like thermal mirrors and blankets rearranging the patterns of solar heating below them. This sudden, widespread change in atmospheric thermodynamics could have created unprecedented instabilities, disrupting normal weather patterns and providing the initial large-scale lift needed to heave the first continent-sized clouds of red dust off the ground. The comet hadn't struck Mars with a hammer. It had poisoned it with a fine crystalline mist, setting in motion a delicate and catastrophic atmospheric alchemy. But there was another, more direct mechanism hidden within the micrometeoroid hypothesis. It wasn't about chemistry, it was about raw energy. Each of those tiny particles, despite being smaller than a grain of sand, was traveling at an astonishing velocity relative to Mars, tens of kilometers per second. While a single impact would be insignificant, the sheer number of them entering the atmosphere simultaneously represented a distributed energy event. It was like a gentle, continuous sandblasting of the entire planet's upper atmosphere over the course of several days. This constant influx of kinetic energy deposited as heat in the tenuous upper layers could have created a thermal anomaly, a warm blanket of air where none should exist. This high-altitude warming would create a pressure differential with the colder layers below a steep gradient that could act like a planetary-scale piston driving powerful vertical winds. These winds, in turn, would have reached down to the surface, providing the mechanical kick, the brute force needed to lift the first critical tons of dust. In this scenario, the comet's tail wasn't a seed for clouds, but a celestial blowtorch, subtly superheating the sky and triggering a convective chain reaction that culminated in a global storm. Both of these micrometeoroid theories were elegant, grounded in known physics, and deeply compelling. Yet they faced a monumental challenge: the complete lack of direct evidence. The proposed instigators, the cometary dust grains themselves, were invisible, their effects theoretical. How could you prove that a planet-wide weather event was triggered by something you could never see or measure directly? It was a ghost story told with the language of astrophysics. The skepticism from the broader scientific community was thick and unforgiving. They demanded proof, not poetry. They pointed to the countless times Mars had experienced global dust storms without the convenient presence of a passing comet. They argued that the Martian atmosphere was a chaotic system fully capable of generating these tempests on its own. To them, this was a phantom cause, a desperate search for an external culprit when the true beast was, and always had been, lurking within the planet's own climate engine. The proponents of the cometary link were at an impasse. They had a beautiful theory, but their hands were empty. They needed a way to test it, a way to turn speculation into something approaching science. This is where the investigation turned inward, away from the skies of Mars and into the glowing heart of humanity's most powerful instruments of simulation. If they couldn't watch the event happen in reality, they would build a new reality from scratch, a digital twin of Mars, a planet of pure data living inside a supercomputer. Teams at planetary science institutes around the world began one of the most ambitious atmospheric modeling projects ever conceived. They fed these computational behemoths everything we knew about Mars: the precise composition of its thin air, the thermal properties of its red soil, the intricate topography of its canyons and volcanoes, and the complex feedback loops that govern its climate. They built a virtual Mars so detailed it could replicate the seasonal ebb and flow of its polar ice caps and the birth of localized dust storms with uncanny accuracy. This digital laboratory, a world built of light and logic, would become the proving ground for their radical ideas. Into this meticulously crafted simulation, they introduced a new variable, a virtual comet. They programmed the precise trajectory of 3I, Atlas, and more importantly, a simulated stream of micrometeoroids matching the density, velocity, and composition expected from such an object. They were about to bombard their digital Mars with the ghost of the real comet. The teams watched for weeks as the simulations ran, churning through trillions of calculations per second. They were peering into a synthetic universe, hoping to catch a glimpse of a chain reaction, a flicker of causality that would validate their suspicions. The early runs were disappointing. In many of the models, the virtual cometary dust did almost nothing. It dissipated into the vastness of the simulated atmosphere, its energy contribution too feeble, its role as a nucleation seed too insignificant to overcome the system's natural stability. The digital planet remained serene, its weather patterns undisturbed. The skeptics, it seemed, were right. The connection was just a beautiful illusion. But a few of the models, the most complex ones that incorporated the most nuanced and cutting-edge understanding of atmospheric microphysics, began to show something. It wasn't a smoking gun. It was a subtle statistical anomaly, a whisper in the data. In these simulations, the introduction of the cometary dust didn't instantly trigger a global storm. Instead, it appeared to prime the system. The models showed a marked increase in the formation of high-altitude ice clouds, just as the nucleation theory predicted. They showed a slight but persistent warming trend in the upper mesosphere, a thermal signature consistent with kinetic energy deposition. The virtual Martian atmosphere became more fragile, more unstable. It was like watching a pile of sand grow steeper and steeper. The comet wasn't the landslide itself, it was the final critical grain that pushed the entire system to the angle of repose, the very brink of collapse. In these simulations, a subsequent normal Martian weather event, a small localized dust devil that would have otherwise died out, cascaded. Fed by the new instabilities created by the cometary dust, it didn't dissipate. It grew, and then it exploded across the virtual globe. This was the turning point. It wasn't proof, not by a long shot. A simulation is not reality, but it was the first glimmer of a plausible pathway. It was a rigorous physics-based demonstration that the idea was not impossible. The models had shown that the delicate, almost imperceptible touch of a comet could, under precisely the right conditions, be amplified by the Martian climate system into a planetary catastrophe. It was a breathtaking example of the butterfly effect playing out on a cosmic scale. The results sent shockwaves through the planetary science community. The debate once confined to the fringes now took center stage. The elegant simulations provided a target, a set of specific atmospheric signatures to hunt for in the real-world data gathered by the flotilla of orbiters circling Mars. Yet even as the micrometeoroid theory gained this fragile foothold, another even more audacious hypothesis was being whispered in the corridors of research centers. It was a theory that relied not on contact but on the most fundamental force in the universe, a force that over the scale of a planet and a comet should have been utterly, laughably insignificant. The investigators started to wonder, could the comet have shaken Mars, not with matter but with gravity? They began to explore the realm of tidal forces. We are all familiar with the moon's gravitational pull on Earth, the engine of our ocean tides. It is a tangible, powerful demonstration of how one body can stretch and deform another across 250,000 miles of space. The question was, could a tiny comet, even at its closest approach, exert any meaningful tidal force on a planet as massive as Mars? On the surface, the answer was a resounding no. The gravitational influence of 3I, Atlas on Mars would have been infinitesimal, thousands of times weaker than the pull of Mars's own tiny moon Phobos. It would be like a fly attempting to budge a battleship. To any classical physicist, the inquiry would end there. The force was simply too small to matter. But the atmosphere is not a solid battleship. It is a fluid, a gossamer-thin shell of gas clinging to the planet, and its behavior is governed by chaos. The proponents of this gravitational theory argued that we were looking at the problem the wrong way. The goal wasn't to physically move the atmosphere in a significant way. The goal was to disrupt its equilibrium. They pointed back to the idea of Mars's climate as a system perpetually on the edge of chaos. Perhaps the comet's gravitational pull, as minuscule as it was, didn't need to be strong, it just needed to be different. It was a new rhythmic perturbation, a gentle push and pull on the atmospheric envelope from an unfamiliar direction. This tidal bulge, however slight, would have propagated through the atmosphere as a wave, a planetary-scale atmospheric tide. Imagine a finely balanced spinning top, a gyroscope of atmospheric pressure zones and wind currents. This system has its own rhythms, its own natural frequencies. The theory proposed that the comet's passing gravitational wave, its tidal whisper, could have resonated with one of these natural frequencies in the Martian atmosphere. This phenomenon, known as resonant forcing, is seen across nature. It's how an opera singer can shatter a wine glass with just their voice, not through raw power, but by matching the glass's natural resonant frequency. It's how you can get a child's swing to go higher and higher with a series of small, perfectly timed pushes. The comet's gravity in this view was that series of perfectly timed pushes on the Martian atmosphere. It was a cosmic nudge, arriving at just the right moment and with just the right rhythm to amplify a tiny pre-existing instability into something monstrous. It could have been the trigger that disrupted the delicate dance of pressure cells, allowing a nascent storm system to break free from its normal constraints and run rampant. This idea was by far the most controversial. It bordered on heresy. The forces involved were so small that they were almost lost in the noise of other, much larger gravitational influences, like the pull of Jupiter or the Sun. Most of the community dismissed it out of hand as a mathematical fantasy. And yet when the modelers attempted to simulate this as well, they once again found a ghost in the machine. When they programmed their virtual Mars to be in a state of extreme atmospheric fragility, a condition known to exist just before the start of the typical dust storm season, and then introduced the faint rhythmic tidal tug of the passing. Virtual Comet, a small percentage of their simulations again, showed the system breaking down. The tiny gravitational perturbation was enough in these specific, finely tuned scenarios to disrupt the polar vortex or alter the flow of the jet stream, creating the seed of a storm that would later grow to global proportions. And so the scientific community found itself fractured, staring at two deeply strange but computationally plausible scenarios. On one side, you had the micrometeoroid camp, with its vision of a planet seeded with celestial dust, a trigger of chemistry and energy from the outside in. On the other, the gravitational camp, with its far more ethereal theory of a resonant whisper, a celestial nudge that caused the planet's own internal demons to be unleashed. Both theories stretched the bounds of known science. Both relied on the core assumption that Mars was an exquisitely sensitive world balanced on a climatic pinhead ready to be tipped into chaos by the faintest of external touches. The rift was no longer between those who believed in a connection and those who did not. It was a deeper, more profound schism between two competing, almost mythical explanations for the same impossible event. The battle lines were drawn. The mystery had only deepened, but for the first time the investigators had a map. They had a set of specific, testable predictions. Now all they had to do was find the evidence, the single, unambiguous fingerprint left behind by the ghost that had passed in the night. And so the intoxicating theory hangs in the air, a spectacular, almost poetic explanation for a world suddenly veiled in red. A celestial visitor, a ghost of ice and rock from the outer darkness, grazes the red planet. In its wake, Mars, which had been slumbering under a thin, placid sky, convulses in a planetary spasm of dust. The timing feels too perfect, too scripted, a piece of cosmic theatre played out over millions of miles. It's a narrative so compelling that we want to believe it. But here, in the quiet, methodical halls of planetary science, wanting is not enough. Here, the burden of proof is a leviathan. The grand, intoxicating hypothesis born in the brilliant light of Comet 3I, Atlas, must now descend from the realm of inspiring speculation into the cold, unforgiving crucible of scientific verification. This is a place where beautiful, elegant ideas are routinely broken against the unyielding wall of evidence, or the maddening lack of it. The first and most imposing challenge is a simple three-word mantra that serves as both the shield and the sword of all scientific inquiry. Correlation is not causation. Just because two events happen in sequence does not mean one caused the other. It is the cardinal rule, the first lesson taught to every aspiring scientist, a safeguard against the human brain's innate desire to find patterns and weave stories where only coincidence may lie. To prove the comet was the trigger, we cannot simply point to the timeline. We must embark on a far more difficult journey, a forensic process of elimination, a meticulous quest to rule out every other suspect. We must prove that Mars would have remained calm, that its skies would have stayed clear had the comet never appeared. We must, in effect, prove a negative across an entire world. The investigation begins with the usual suspects, the known instigators of Martian atmospheric turmoil. These are the forces planetary scientists have studied for decades, the well-understood gears of the Martian weather engine. First on the list is the Sun itself. Mars travels on a highly elliptical orbit, a path that brings it significantly closer to the Sun at a point we call perihelion. During this phase, the planet drinks in substantially more solar energy, a flood of warmth that can profoundly destabilize the delicate atmospheric balance. This surge in heat doesn't warm the planet evenly. It strikes the southern hemisphere then at the height of its summer with a focused intensity. The ground heats up, and the air just above it grows buoyant and restless. This temperature difference between the surface and the frigid air aloft creates powerful convective currents, vast, upward spiraling columns of air that can act as the initial pistons in the engine of a dust storm. Could this be our culprit? Was the global storm of 2018 simply Mars, running on its predictable solar-powered schedule? Teams around the world dive into the data, constructing intricate computer models that simulate the solar energy budget of Mars for that specific year. They map the incoming radiation factor in the surface reflectivity, the atmospheric transparency, and the precise orbital mechanics. The models churn through trillions of calculations, recreating a virtual Mars to see if it would spontaneously generate a planet-encircling event under those conditions alone. The results are ambiguous. Yes, the solar forcing was strong as expected near perihelion. It certainly provided the baseline energy, the raw fuel for atmospheric chaos. But the models struggle to consistently produce a storm of this magnitude, this speed, this ferocity. Something seems to be missing. The engine was primed, but some unknown spark appears to have provided the final critical ignition. The Sun is a powerful accomplice, but perhaps not the primary architect of this particular disaster. With the most obvious suspect failing to confess, the investigation turns to a more subtle, yet equally powerful force, the phenomenon of thermal tides. This has nothing to do with oceans, but everything to do with the atmosphere behaving like one. As Mars spins on its axis, the side facing the Sun heats up dramatically, causing the thin air to expand and rise. On the cold night side, the atmosphere cools, contracts, and sinks. This daily cycle of heating and cooling creates massive planet-scale waves of pressure and wind that flow across the globe, a rhythmic breathing motion of the entire atmospheric envelope. These are the thermal tides, and their power is immense. They can generate winds that circle the planet at hundreds of miles per hour, especially in the middle and upper atmosphere. These tides are the great organizers of Martian weather, the unseen hand that shapes the planet's winds into predictable patterns. Sometimes these patterns can align in a perfect storm of constructive interference. Waves of wind reinforcing one another can focus their energy on a specific region, creating a localized vortex powerful enough to lift the first fine grains of dust from the surface. This is a leading theory for how regional dust storms get their start. So, the planetary detectives begin their second line of inquiry. They meticulously analyze the atmospheric temperature and pressure data from the Mars Reconnaissance Orbiter and other probes. They are searching for the signature of an unusually powerful or perfectly aligned set of thermal tides in the days leading up to the storm's genesis. Was there a unique resonance, a once-in-a-century atmospheric chord that was struck, providing the necessary energy to kickstart the cascade? Again, the evidence is tantalizing but not conclusive. The tides were certainly active, their rhythmic pulse a constant feature of the Martian sky. There were fluctuations, moments of heightened energy, but nothing that screamed with unassailable certainty, "I am the cause." There was no single overwhelming tidal event that could be definitively pointed to as the trigger. The data shows a system under stress, a system ripe for disruption, but the fingerprint of the primary culprit remains maddeningly elusive. The case is growing colder. The focus then shifts from a single planet-scale trigger to a more chaotic bottom-up scenario, the cascade effect. Global dust storms on Mars don't always begin as a singular monstrous event. Often they are born from the merger of smaller regional storms. Imagine it as a series of wildfires in a dry forest. A small, localized storm kicks up dust in one region, say the vast plains of Acidalia planitia. This plume of suspended dust does something crucial: it absorbs sunlight. The dust particles themselves heat up, warming the column of air around them. This pocket of warm air, now more buoyant than its surroundings, begins to rise, creating a low-pressure zone underneath it, and drawing in more wind from the cooler, clearer areas nearby. These new, stronger winds lift even more dust, which in turn absorbs more sunlight, which heats the air further, which creates even stronger winds. It is a runaway feedback loop, a self-perpetuating dust-fueled heat engine. Now, picture dozens of these smaller storms erupting across a hemisphere, each one a growing engine of wind and dust. If the conditions are right, these storms can expand until they meet their energies, combining their dust clouds, merging into a single, unstoppable weather front. This is the cascade, the process by which a collection of regional skirmishes can escalate into a planetary war. To investigate this, scientists become storm trackers on a world 200 million miles away. They rewind the satellite imagery, poring over daily global maps from the weeks before the event. They are looking for the seeds of the eventual monster, the telltale signs of multiple smaller storms growing and moving in concert, and they find them. There were indeed several significant regional storms brewing in the southern hemisphere. The storm that would eventually become the global Leviathan did appear to absorb one or two smaller systems as it grew. For a moment, this seems like the most plausible, the most conventional, the most Martian explanation. It fits the established pattern. But once more, a shadow of doubt lingers. The speed of the escalation was breathtaking, faster than most models of storm mergers would predict. The storm didn't just grow, it exploded. It seemed to possess an energy, a vitality that went beyond the simple sum of its parts. The cascade theory explains the mechanics of growth, but like the other suspects, it struggles to account for the sheer, unbridled ferocity of that initial eruption. The conventional explanations, while all contributing factors, feel like they are describing the kindling, the dry wood, and the prevailing winds. They do not explain the match. Having found no definitive culprit within Mars itself, the investigation must now turn outward toward the comet. The burden of proof shifts dramatically. It's no longer enough to cast doubt on the usual suspects. Now we must find positive, direct physical evidence of the comet's influence. We are no longer looking for a familiar Martian fingerprint. We are now hunting for an alien one. This is where the challenge moves from the complex to the nearly impossible. You are searching for the ephemeral traces of a ghostly encounter, a fleeting interaction that happened high in the most tenuous layers of the atmosphere. What would such a smoking gun even look like? The first place to hunt is in the realm of the unseen, in the electrical environment of the upper atmosphere. A comet is not just a dirty snowball, it is a source of plasma. As it nears the sun, its ices vaporize, and the solar wind, a stream of charged particles, slams into this expanding gas cloud. The interaction strips electrons from the atoms and molecules, creating a vast, magnetized tail and coma of ionized gas. When this cloud of charged particles swept past Mars, it would have plowed into the planet's own thin upper atmosphere, its ionosphere. The interaction should have been violent on a microscopic scale. It would be like a celestial blowtorch momentarily searing the top of the Martian sky. This event would have injected a tremendous amount of energy and charged particles, creating a widespread anomalous ionization event. It would have left an electrical scar. Our best tool for finding such a scar is the MAVEN spacecraft, NASA's Mars Atmosphere and Volatile Evolution mission. Its entire purpose is to study the Martian upper atmosphere and its interaction with the Sunday. MAVEN's instruments are designed to taste the ions, to measure the magnetic fields, to map the flow of charged particles. If the comet's plasma tail delivered a significant electrical jolt, MAVEN should have seen it. And so teams of physicists begin the painstaking task of sifting through terabytes of MAVEN data from the precise window of the comet's closest approach. They are looking for a sudden, inexplicable spike in electron density, a bizarre fluctuation in the ionospheric currents, a telltale ripple in the planet's weak, patchy magnetic field. They search for days, then weeks. They process and reprocess the data, filtering out the constant noise from the solar wind, looking for anything that stands out as truly unique, truly cometary. But the ghost remains elusive. There are small fluctuations, tiny wiggles in the data streams, but nothing that rises above the background noise with enough certainty to be declared the definitive signature of a cometary impact. The electrical scar, if it was ever there, was either too faint to be detected, or it has been erased by the constant subsequent buffeting of the solar wind. The first search for the comet's fingerprint comes up empty. The hunt then moves from the electrical to the chemical. If the comet's plasma didn't leave an electrical trace, perhaps its dust and gas left a chemical one. The tail of a comet is a cocktail of exotic materials, a chemical soup brewed in the deep freeze of the outer solar system. It contains not just water ice and carbon dioxide, but also more complex organic molecules, strange isotopes of common elements and minerals not typically found in the Martian atmosphere. As Mars passed through this tenuous tail, it should have vacuumed up some of this material. The cometary dust and gas would have rained down through the upper atmosphere, a microscopic, invisible meteor shower. Could we find these alien contaminants? This is a job for the European Space Agency's Trace Gas Orbiter, or TGO. As its name implies, TGO is the ultimate atmospheric sniffer. Its spectrometers are so sensitive they can detect chemical compounds present in mere parts per billion. It is designed to hunt for the faintest chemical whispers in the Martian air, searching primarily for methane and other gases that could be signs of life. But for this investigation, its mission is repurposed. Scientists instruct the orbiter to hunt for the chemical signature of 3I, Atlas. They are searching for a sudden temporary spike in atmospheric water vapor at high altitudes far higher than where Martian water is usually found. They look for specific sulfur compounds, or complex carbon chains known to exist in comets. The task is monumentally difficult. You are trying to find a handful of alien molecules mixed into an entire planet's atmosphere. It is the equivalent of trying to find a single unique grain of sand scattered across all the beaches of Earth. The TGO data is a labyrinth of complex spectral lines, each peak and trough representing a different chemical absorbing light. The team must build a model of what the normal Martian atmospheric spectrum should look like and then subtract it from the data they collected during the flyby. They are searching for what's left over, the anomaly, the chemical echo of the comet. They run the analysis, they check their calibrations, they compare the results to data from before and after the event, and once again the result is agonizingly inconclusive. There are hints, faint possibilities. A tiny, statistically insignificant blip in the water vapor readings at one altitude, a spectral line that could, with some generous interpretation, be attributed to a cometary organic. But there is nothing clear, nothing definitive, no unassailable chemical proof that screams the comet was here. The frustration among the research teams is palpable. Every logical path to finding evidence leads to a dead end. The grand cosmic drama seems to have unfolded without leaving a single readable page of its script behind. This is the brutal, often hidden reality of the scientific process. It is not always a story of dramatic eureka moments and sudden breakthroughs. More often, it is a slow, grinding advance through a fog of ambiguity. It is the exhaustion of staring at screens of data until your eyes blur. It is the quiet disappointment of a promising lead that evaporates under closer scrutiny. It is the discipline to resist the allure of a beautiful theory when the data refuses to support it. The debate within the scientific community intensifies. One camp argues that the lack of evidence is itself evidence of absence. The timing was a coincidence, they say, a once-in-a-billion-years fluke. Mars was going to have a global storm anyway, and the comet was merely a spectacular but irrelevant bystander. The other camp holds fast. They argue that our instruments simply weren't sensitive enough, or weren't in the right place at the right time to capture the fleeting evidence of the interaction. The trigger they propose may have been a more subtle phenomenon than a simple electrical jolt or chemical deposit, a complex cascade of events in the upper mesosphere that our current models don't even account for. They argue that the sheer improbability of the coincidence demands that we keep looking, that we refuse to dismiss the connection just because the first few searches came up empty, and so we are left in a state of profound and fascinating uncertainty. We have a planetary scale mystery, a potential connection that could rewrite our understanding of how worlds interact with their cosmic environment, yet we stand before it with empty hands. The conventional suspects have shaky alibis, and the prime suspect, the interstellar interloper, has left no fingerprints. The path to proving causation has led us not to a clear answer but deeper into a maze of complexity. The deeper we look, the less we seem to know for sure. To solve this puzzle, we may need to look not for a single piece of evidence but for a different kind of pattern, a more subtle clue hidden somewhere in the storm itself. Is it possible the storm's behavior, its very character, was fundamentally altered by its otherworldly trigger? For months, the global scientific community had held its collective breath. Across countless institutions in darkened labs, illuminated only by the glow of data streams, a digital vigil was kept. The world's most sophisticated minds had been locked in a silent, frantic race against uncertainty, sifting through an avalanche of information beamed back across the gulf of space. They were searching for a ghost in the machine, a whisper of a connection in a symphony of planetary chaos. Now the silence was beginning to break, not with a single sudden announcement, but with a growing chorus of consensus, as independent teams working in isolation began to arrive at the very same startling destination. The time for speculation was over. The era of evidence had arrived, and it demanded a final reckoning with the question that had haunted our exploration of Mars. Did a visitor from another star system wound the red planet? The first and most tantalizing hypothesis to face the cold scrutiny of data was the most direct, the idea of physical seeding. The theory was seductively simple. Comet 3I, Atlas, in its majestic sweep past Mars, could have shed a trail of its own primordial dust, a fine interstellar powder that drifted into the upper atmosphere. Each microscopic grain, a stranger to our solar system, could have acted as a nucleus, a tiny anchor around which Martian water ice or atmospheric dust could coalesce, triggering a cascade of cloud formation and atmospheric disturbance that avalanched into the global storm we witnessed. To prove it, scientists needed to find the cometary DNA, the chemical fingerprint of 3I. Atlas mingled with the native red dust of Mars. They began the hunt. On board the Mars atmosphere and Volatile Evolution Orbiter, or MAVEN, an instrument known as the Neutral Gas and Ion Mass Spectrometer, was our primary detective. It had been tasting the thin Martian air for years, building an exhaustive library of its chemical composition. As the storm raged and then subsided, MAVEN dipped low, skimming the atmospheric boundary, inhaling molecules for analysis. Scientists were looking for telltale isotopic anomalies. In the vast cosmic nurseries where stars are born, the ratio of certain elements and their isotopes like deuterium to hydrogen can be vastly different from what we find in our own solar system. Finding a spike in these exotic ratios within the Martian atmosphere during or after the comet's passage would have been the smoking gun, an undeniable link. Day after day, the data poured in clean and unambiguous. The spectrometer's readings were meticulously charted against the baseline, the established chemical signature of Mars. There were no spikes, no alien whispers. The deuterium to hydrogen ratio remained stubbornly, unshakably Martian. The composition of the upper atmosphere, even as it was churned by the planet-girdling tempest below, showed no trace of contamination, no hint of an interstellar intruder. The ghost was not in the air. Perhaps then the evidence was on the ground. As the great storm finally calmed and the thick haze began to settle, a fine layer of dust coated the entire planet, a fresh red blanket laid over the landscape. On the surface, our tireless robotic geologists, Perseverance and Curiosity, were waiting. Their sophisticated onboard laboratories, the ChemCam and Sherlock instruments, were designed to probe the chemical makeup of Martian rocks and soil with laser precision. They were tasked with a new mission to analyze this fresh layer of dust, the very fallout from the heart of the storm. They zapped sample after sample, vaporizing tiny specks of dust and analyzing the light signatures of the resulting plasma. Once again, the search was for the exotic, for anything that did not belong. They hunted for unusual mineralogies, for chemical compounds rich in the volatile iks one would expect from a comet's nucleus. The result was a resounding planet-wide confirmation of Maven's findings. The dust was purely, authentically Martian. It was the same iron-rich basaltic material that has colored the planet for billions of years. In the silent chambers of our most advanced planetary labs, the verdict was delivered not with a bang, but with a persistent, unwavering whisper of no. The chemical fingerprints they hunted, the exotic isotopic ratios that would scream interstellar, were simply absent. The comet, it seemed, had passed without leaving so much as a single grain of its stardust behind. The most direct and dramatic link had been severed. With the theory of direct material seeding dismantled, investigators turned their attention to the invisible forces at play. A comet is not merely a dirty snowball, it is an electrified, dynamic body. As 3I Atlas neared the Sun, it developed a vast coma and a magnificent plasma tail, a stream of charged particles bleeding off into space, interacting with the solar wind. Mars, unlike Earth, lacks a global magnetic field to protect it. It has only remnant pockets of magnetism fossil fields locked in its ancient southern crust. The hypothesis was compelling. Could the comet's electrically charged passage have zapped the Martian ionosphere? Could this immense electromagnetic disturbance have injected a colossal amount of energy into the atmosphere, creating atmospheric lightning or a thermal shockwave powerful enough to kickstart a storm of planetary proportions? This was a crime scene for plasma physicists. Maven once again was the key witness. Its suite of instruments is designed explicitly to measure the magnetic and electrical environment around Mars. As 3I Atlas made its closest approach, Maven was watching, recording every fluctuation in the planet's magnetic field, every change in the density and temperature of its ionospheric plasma. The datasets were immense, capturing a moment-by-moment account of the interaction. When the analysis was complete, the story it told was one of cosmic subtlety, not brute force. Yes, there was an interaction. The instruments detected faint ripples, minor perturbations in the local plasma environment as the comet's magnetic influence washed over Mars. Faint, localized auroras, the ghostly Martian equivalent of our northern lights, flickered a little more brightly over the southern crustal fields, but the scale of the event was profoundly underwhelming. The energy deposited into the Martian atmosphere by the comet's passage was minuscule orders of magnitude, less than the energy Mars receives from a typical solar flare or coronal mass ejection from our own Sunday. It was, in the words of one lead scientist, like trying to start a forest fire with a single sparkler in the middle of a rainstorm. The comet's electrical influence had been a celestial ghost passing through the planet's magnetic house without so much as rattling a window. The atmospheric engine of Mars had barely registered its presence. The electrical trigger theory, so elegant in its conception, had dissolved under the weight of hard numbers. Two major hypotheses had now been tested and found wanting. The investigative net was cast wider still into the realm of the truly subtle. Perhaps the influence was neither chemical nor electrical, but gravitational and thermal. A body as massive as 3I, Atlas, even at a distance, exerts a gravitational pull. Could this tidal force have created a pressure wave, a ripple in the thin Martian air that was amplified into the genesis of a storm? Furthermore, the comet's enormous bright coma of gas and dust is highly reflective. It acts like a giant dusty mirror in space. Could it have focused a beam of sunlight onto a specific region of Mars, creating a thermal pulse, a sudden spot of warming that destabilized the atmospheric column below it? Here, direct measurement was impossible. This was the domain of the supercomputer. Teams of atmospheric modelers and orbital dynamicists constructed the most detailed simulations of the encounter ever attempted. They fed, in the precise observed trajectory of 3I, Atlas, its size, its brightness, its rate of outgassing. They coupled this with our most sophisticated models of the Martian atmosphere, intricate programs that simulate wind pressure and temperature on a global scale. They ran the encounter again and again in digital form 1,000 times over tweaking variables to see if any plausible scenario could lead to a storm. The results were a final categorical refutation. The gravitational tug of the comet on the Martian atmosphere was found to be less than the pull exerted by Mars's own tiny moon Phobos. It was a gravitational whisper so faint it was lost in the daily atmospheric tides driven by the Sunday. The thermal pulse, the focused beam of sunlight, was similarly insignificant. The simulations showed that any localized heating from the comet's reflection would have been less than 1/10 of a degree Celsius, an amount completely dwarfed by the dramatic day-night temperature swings that Mars experiences every single sol. The digital Mars remained placid. The models refused to generate a storm. No matter how they configured the encounter, the comet was simply too far away, its influence too fleeting, its energy contribution too small to be the trigger. The investigation had reached a turning point. Every proposed mechanism of interaction, from the direct to the esoteric, had been systematically dismantled by evidence. A sense of profound scientific anticlimax began to set in. Was this it? Was the entire terrifying, beautiful spectacle nothing more than a coincidence? But it is often in such moments, when every expected answer turns out to be wrong, that science makes its greatest leaps. The relentless elimination of external causes forced the entire research community to do something radical, to turn away from the comet completely and look back at Mars itself, but with a new, intensely focused vision. The central question was reframed. It was no longer, did the comet cause the storm? The new question, the far more powerful question, became, what was happening on Mars that made it so perfectly, so exquisitely primed for a global dust storm at that exact moment in history? The unprecedented observation campaign, mobilized to study, potential alien influence, had inadvertently created the most comprehensive dataset on the birth of a purely Martian phenomenon ever assembled. The scientists had been watching for a murderer, but in doing so, they had filmed a natural birth in stunning high-definition detail. And in that data, the real story began to emerge, a story of a planet's internal rhythms of seasonal power and delicate feedback loops. The emerging consensus was that the global dust storm was the culmination of a wholly Martian process, a planetary perfect storm. The first and most critical factor was timing. The comet's passage had coincided with the peak of the Martian southern summer. This is when Mars is at its perihelion, its closest point to the Sun in its elliptical orbit. Solar radiation was at its absolute maximum, pouring energy into the southern hemisphere, heating the surface and the lower atmosphere, creating the maximum possible temperature contrast with the cold, winter-bound north. This differential is the fundamental engine of Martian weather, the primary fuel source for its winds. The planet was in a sense already at a full boil. Second, the high-resolution imagery captured in the weeks leading up to the main event revealed the precursors. For years, scientists had theorized that global storms don't just appear from nothing, they grow from the merging of smaller, localized storms. The constant watch for cometary effects allowed them to see this theory play out in reality. Orbiters tracked dozens of smaller dust storms, dust towers, that punched high into the atmosphere across the southern plains. They watched as these separate systems, driven by the intense seasonal heating, began to drift and coalesce like tributaries flowing together to form a mighty river. This was the kindling being gathered, the stage being set for a much larger conflagration. The planet was actively preparing itself. The final crucial piece of the puzzle was the confirmation of a powerful positive feedback loop. This is the mechanism that allows a regional storm to become a global monster. As the merging storms grew larger, they had enough power to lift dust not just a few kilometers, but tens of kilometers into the thin atmosphere. Up there, the dark reddish dust particles are incredibly efficient at absorbing sunlight. Instead of the sunlight reaching the ground, it was now being trapped high in the atmosphere, heating that layer of air directly. This created an even starker temperature contrast with the layers below it, generating more violent winds, which in turn lifted even times more times dust, which then absorbed even times more times sunlight. It was a runaway process, a self-perpetuating atmospheric chain reaction. Once a critical threshold was crossed, the storm began to feed itself, growing exponentially until its dusty tendrils had wrapped themselves around the entire globe. The intense continuous monitoring meant for the comet allowed scientists to measure the atmospheric temperature changes and wind speeds inside this feedback loop with a precision they had only dreamed of. The final verdict, peer-reviewed and published in a flurry of papers, was as profound as it was unexpected. Comet 3I, Atlas, did not cause the 2038 global dust storm. It was an innocent, if spectacular, bystander. The two events were two colossal independent dramas that by a staggering cosmic coincidence unfolded on the same celestial stage at the same time. It was a coincidence of such improbable scale that it forced us to mobilize the full might of our interplanetary scientific resources, and in doing so it gave us the greatest gift imaginable. The legacy of this event is not one of a mysterious cometary interaction. The legacy is the data. Because we were looking for a connection, we watched Mars more closely than ever before. We now possess the most complete record of the genesis of a global dust storm in human history. Our predictive models for Martian weather have been revolutionized, jumping forward a generation in their accuracy. For the first time, we truly understand the anatomy of these planet-altering events, the seasonal prerequisites, the precursor storms, the terrifying physics of the feedback loop that drives them. This knowledge is not academic. It is the key to our future on Mars. For the first astronauts who walk that red soil, a global dust storm is not a scientific curiosity. It is a mortal threat. It can blot out the sun for months, rendering solar power useless and plunging the world into a frigid ochre twilight. The ability to predict the onset of the next great darkening is a fundamental requirement for the survival of any future human colony. Thanks to a chance alignment with a visitor from the stars, we are now closer than ever to possessing that ability. The investigation that began with a search for an external aggressor ended with a moment of profound self-knowledge about our neighbor world. We looked for the influence of a comet, but what we found was the very heartbeat of Mars. And so we stand at the end of a long and winding road, a path of inquiry that began with a breathtaking, almost unbelievable cosmic tableau. We started with two titans locked in an apparent impossible conversation across millions of kilometers of silent space. One, an ancient world wrapped in a furious ochre-colored shroud of its own making. The other, a ghostly visitor from the abyss, a transient messenger of ice and rock, trailing its spectral hair against the black. The alignment felt too perfect, too poetic to be mere chance. It was a celestial coincidence so profound that it demanded an explanation, compelling us to look closer, to sift through terabytes of data, and to question our most fundamental assumptions about the forces that shape a planet's destiny. You have traveled with us through the digital eyes of orbiters and rovers, peered into the complex heart of atmospheric models, and followed the spectral breadcrumbs left by a disintegrating comet. The initial question was simple, stark even. Did the passage of Comet 3I, Atlas, this interstellar wanderer, somehow ignite the global dust storm on Mars? Did this silent flyby have the power to awaken the sleeping giant of the Martian, climate? Now, after piecing together the puzzle, we can finally look back, not with just wonder, but with the clarity of understanding. The answer, as we have discovered, is not a simple yes or no. It is a story far more intricate, a tale of a world already pushed to the brink, receiving a final, almost imperceptible nudge from the cosmos. The conclusion we have reached is a testament to the subtle, interconnected nature of our solar system, a place where the faintest whisper can, under the right conditions, unleash a symphony of chaos. What we have definitively learned is that Mars was a world primed for catastrophe, a planet wound like a spring waiting for the slightest touch to release its stored energy. Our journey took us deep into the planet's seasonal rhythms, revealing a climate system of immense complexity and delicate balance. We saw how over the preceding months, a series of regional dust storms near the northern polar cap acted as a kind of atmospheric preamble. These were not random tempests. They were the planet's circulatory system in action, lifting fine particulates into the thin air, seeding the atmosphere with the very material that would later fuel the global inferno. You saw the data from the Mars Climate Sounder, which showed a critical buildup of atmospheric dust, creating a feedback loop where suspended dust absorbed sunlight, heated the air around it, and generated even stronger winds to lift more dust. This process had been escalating, creating a precarious state of atmospheric instability across the entire northern hemisphere. Mars, it turns out, was already on a knife's edge. The baroclinic waves, those vast continent-sized weather systems, were growing in intensity, their swirling energies churning the atmosphere. The pressure gradients were steepening, the thermal tides growing more extreme. The planet was holding its breath, and the evidence suggests it would have likely exhaled into a major storm season regardless. But the scale, the sheer planet-enveloping totality of what occurred, still begged for an external catalyst, a final piece of the puzzle that could explain the ferocity and the timing of the storm's ignition. It required us to look up, away from the red dust, and out into the blackness of space, toward the silent passage of that icy phantom. The Comet 3I, Atlas, was not a passive observer. Our investigation has revealed it to be an active participant in this grand drama, its influence delivered through a cascade of subtle yet powerful mechanisms. The most direct and perhaps most astonishing of these was the microscopic rain of cometary dust. As Atlas neared the Sun, it was not merely a solid body. It was a celestial engine of sublimation, shedding gas, and crucially vast quantities of fine-grained dust. We followed the complex orbital mechanics, modeling how this stream of debris, an invisible river of cosmic grit, would intersect with Mars's path. The result was a planetary-scale meteor shower of unprecedented subtlety. These were not brilliant fireballs streaking across the sky, but a persistent, almost gentle influx of nanoscopic particles. When these high-velocity specks entered the upper Martian atmosphere, they acted as perfect condensation nuclei. Each tiny grain became a seed, an anchor point around which water ice crystals could form with extraordinary efficiency. We saw this in the spectroscopic data, a sudden, anomalous spike in high-altitude noctilucent clouds, shimmering electric blue against the twilight terminator. These clouds were not merely beautiful, they were a profound thermodynamic engine. By reflecting sunlight back into space, while trapping thermal radiation rising from below, they dramatically altered the temperature balance of the mesosphere. This sudden cooling of the upper atmosphere and subsequent warming of the layers below created a powerful destabilizing effect, a vertical shockwave of energy that rippled downwards, providing the critical perturbation needed to switch on the already unstable lower atmosphere. The comet, it seems, seeded the Martian sky, not just with ice, but with the very genesis of the storm. Beyond this direct seeding, Atlas exerted its influence through a far more ethereal medium, its colossal hydrogen coma. As sunlight fractured the water molecules sublimating from the comet's nucleus, it created an enormous invisible cloud of hydrogen gas, an atmospheric halo stretching for millions of kilometers. When Mars plowed through this tenuous envelope, its own atmosphere was temporarily but significantly enriched with this light reactive element. We watched the models from MAVEN, the Mars atmosphere, and Volatile Evolution Orbiter as they processed this new variable. The influx of hydrogen had a cascading chemical effect. It reacted with the oxygen and ozone in the thin Martian air, disrupting the delicate photochemical balance that governs atmospheric heating and cooling. This process subtly altered the thermal properties of the middle atmosphere, changing how it absorbed and radiated energy. Think of it as slightly changing the tint on a global greenhouse window. The effects are not immediate or dramatic, but they accumulate, creating pockets of unexpected heating and cooling that further disturb the atmospheric equilibrium. It was a form of celestial chemical warfare on a planetary scale, a silent, invisible invasion that tweaked the very chemistry of the air, adding yet another layer of instability to a system already begging to collapse. This hydrogen breath from a passing ghost was another push, another nudge towards the inevitable. The comet wasn't just a physical presence, it was a chemical one, leaving a transient but powerful imprint on the world it passed. Finally, we uncovered the most ghostly interaction of all, a phenomenon that occurred in the invisible realm of magnetic fields and charged particles. Mars, lacking a global magnetic field like Earth's possesses, only localized remnant fields embedded in its crust magnetic islands in a sea of vulnerability. The solar wind, that constant stream of particles from our sun, normally interacts directly with the Martian upper atmosphere, creating a complex induced magnetosphere. But the arrival of Comet Atlas introduced a new and disruptive player. Comets generate their own magnetotails, vast turbulent structures carved out of the solar wind by the comet's own outgassing and plasma. As Mars passed through the wake of Atlas, it was buffeted by the comet's turbulent, flickering magnetic tail. This was not a physical collision, but an electrodynamic one. The sensitive magnetometers aboard our orbiters registered the disturbance, a sudden chaotic fluctuation in the magnetic environment around Mars. This magnetic tremor propagated downwards, energizing particles in the ionosphere and creating atmospheric gravity waves. These waves, ripples of pressure and density, traveled through the thin upper air, like waves on a pond carrying energy from the edge of space down into the heart of the weather-making regions below. This final energetic injection from the comet's magnetic passage may have been the most delicate of all its influences, yet it was perhaps the definitive one. It was the snap of the fingers, the energetic impulse that synchronized the disparate regions of atmospheric instability, allowing the localized storms to merge and erupt into the single planet-girdling monster we witnessed. The evidence, when taken together, paints a compelling portrait. Mars was the powder keg, but the comet, through its dust, its gas, and its magnetic wake, provided the spark. The implications of this discovery ripple outwards, fundamentally altering our perception of Mars and its place in the cosmos. For decades, we have modeled the Martian climate as a largely closed system, a world governed by its own orbital tilt, its eccentric orbit, and the energy output of the Sun. We are now forced to see it as something more, a planet susceptible to the whims of interstellar traffic. Its climate is not an isolated laboratory, but an open ecosystem, one that can be touched and changed by the passage of bodies from the darkest, coldest reaches of the solar system. This realization has profound consequences for our future with the Red Planet. When we send human explorers to Mars, we must now account for this new variable. A long-period comet discovered only months before its closest approach could become a critical factor in mission, planning its passage, potentially heralding a period of extreme and dangerous weather. The dust storms we must prepare for are not just seasonal, they may also be cometary. Furthermore, this discovery forces us to look back into Mars's deep past with new eyes. During the late heavy bombardment, when the inner solar system was a chaotic shooting gallery of comets and asteroids, could such interactions have been commonplace? Could frequent cometary passages have played a significant role in shaping Mars's ancient climate, perhaps contributing to the stripping of its atmosphere? Or, conversely, delivering the very water and organic compounds we now search for? The ghost of Atlas prompts us to rewrite not only our predictions for the future, but our interpretations of the past. This newfound understanding of planetary interconnectedness extends far beyond the orbit of Mars. It serves as a powerful reminder that no world is an island. We have witnessed a direct causal link between a body from the Oort cloud and the weather on a terrestrial planet. We are now compelled to ask, what other subtle connections have we missed? How does the powerful magnetic field of Jupiter affect the atmospheric chemistry of its moons in ways we don't yet understand? What role does the fluctuating stream of interstellar dust, which our solar system periodically drifts through, play in the climates of the outer gas giants? The universe, it seems, is bound by invisible threads, a web of gravitational, chemical, and electrodynamic influences that we are only just beginning to map. The encounter between Mars and 3I, Atlas, has provided us with a Rosetta Stone for deciphering these interactions. It teaches us that to understand a single planet, we must understand the neighborhood it lives in, the traffic that passes through it, and the ghostly whispers it is subjected to from distant travelers. It has transformed planetary science, shifting the focus from isolated systems to a more holistic, integrated view of the solar system as a single interacting entity. Every asteroid, every comet, every Kuiper Belt object is not just a point of light, but a potential agent of change, a messenger carrying clues about the dynamic, interwoven nature of our cosmic home. To grasp this new dynamic reality, we must look to the future, to a new era of observation and prediction. The challenge laid down by this event is clear. We need to see farther, model with greater complexity, and monitor with more vigilance than ever before. On the horizon are next-generation orbital assets for Mars fleets of satellites working in concert, not just as individual experiments, but as a unified planetary sensor web. They will carry advanced LiDARs to map dust profiles in 3 dimensions, sophisticated spectrometers to track chemical changes in real time, and magnetometers sensitive enough to detect the faintest cosmic disturbances. This orbital network will provide a continuous high-fidelity health check of the Martian atmosphere, allowing us to spot the telltale signs of instability long before a storm erupts. Simultaneously, our ability to track potential instigators like Comet Atlas is poised for a revolutionary leap forward. Telescopes like the Vera-C Rubin Observatory will soon begin their survey of the sky, cataloguing millions of small bodies with unprecedented speed and precision. Its nightly scan of the heavens will create a motion picture of the solar system, allowing us to identify and project the trajectories of potentially influential comets years, even decades in advance. This early warning system is paramount, but observation alone is not enough. The true predictive power will come from the fusion of this new data with the next generation of supercomputing. We will build digital twins of Mars' complex atmospheric models that are no longer isolated but are integrated into a larger simulation of the inner solar system. These models will be able to simulate in exquisite detail the precise effects of a comet's passage. They will ingest the comet's observed outgassing rate, its dust composition, and the structure of its plasma tail, and then project how these factors will interact with a real-time model of the Martian atmosphere. We will be able to run scenarios to ask the model, what happens if a comet of this size passes at this distance? The goal is to move from reactive analysis to proactive forecasting, to be able to predict not just that a dust storm is likely, but that a specific times cometary encounter has a high probability of triggering a global event. This synergy of comprehensive observation and sophisticated simulation represents the future of planetary defense, not from impacts, but from these more subtle climate-altering interactions. It is a future where we are no longer surprised by the silent influence of passing ghosts, but can anticipate their arrival and understand their consequences. This is not science fiction. It is the necessary next step in our evolution as a multi-planetary species, a step toward becoming true custodians and caretakers of our corner of the cosmos. We began this journey with a sense of awe, with the humbling spectacle of a world in turmoil and a visitor from the void. We end it with something more profound, a deeper appreciation for the intricate, often invisible tapestry of the universe. The story of the Martian global dust storm and Comet 3I, Atlas, is more than a fascinating scientific detective story. It is a parable for the nature of discovery itself. It reminds us that the cosmos is not a static museum of predictable clockwork objects, but a living, breathing, interacting system of staggering complexity. It proves that even phenomena that appear to be mere coincidences, beautiful but meaningless alignments, can be gateways to a new and richer understanding. They are the universe's way of inviting us to look deeper, to challenge our assumptions, and to find connections where we thought none existed. The spirit of human curiosity, that relentless drive to ask why, is our primary tool for navigating this intricate reality. It is the engine that propelled us from staring at a dusty red dot in the sky to understanding the delicate chemistry of its atmosphere. It is the same fire that will push us to build the next generation of telescopes and probes, to write the next lines of code for our planetary models, and to one day walk upon that red soil ourselves. The universe is constantly whispering its secrets. Our great and enduring adventure is, and always will be, learning how to listen.